Okay, guys, I think we'll get started, if that's okay with you. Um, all right, so my name is Aaron Maguire. I'm the application engineer from Donaldson Filtration, and I'm from Ireland. So if you can understand my English okay, then you're doing pretty well. Um, so I studied mechanical engineering in Ireland, and I started recently with Donaldson about 7 months ago. And my job has been to release new parts for the aftermarket, which is spare engine parts. And today I'll be talking about Clean Solutions, which is a range of products that we have that are aimed at an efficiency concept that we like to call clean, protect and polish. So I'll give you a quick rundown of how the presentation will go, which is I'll run you through the clean, protect and polish concept, how it works, how we approach it, what each of the clean, protect and polish parts of the concept are, and then I'll run you through contaminants, how they affect your machines, what they are exactly, how they form, and how we deal with those. Then I'll run you through the importance and effect of clean solutions, how it can be used in the field, what regulations there are regarding this, and what wear and tear it can cause to an engine. And then finally, I'll run you through a case study of a mine that we've applied clean solutions to and the savings that they make because of Donaldson's clean solutions approach. So the efficiency concept is that we reduce downtime, reduce maintenance costs, and we pre-clean all fluids before they enter an application. What does this mean? It means that you have a longer uptime on your service intervals, you have lower replacement part costs because you replace less parts every time you do a service, and you have your on-application filters which last longer. When we clean air for an application, we like to say that we have two-stage air cleaning, and that is that some of the air particles, the particles that are in the air, are pre-cleaned, so the larger particles are taken out by a process, a centrifugal process, and it's a similar concept when we apply this to liquids. We like to pre-clean the fluids so that the actual filter, the media, lasts longer. So how does the clean, protect and polish system work? The approach is that we have a manifold that's placed before your storage tanks, and this is to take as much dirt as possible out before the fluids go into storage. So that's all fluids, including fuels, diesel fuels, hydraulic fluids and lube oils, heavy gear oil as well. So when it's stored in the tank, we obviously want to keep it clean. So once it's been filtered once, we look at the spin-ons and everything on the first one. But then we have a different approach for keeping it clean while it's in the tank. And the main contaminant that we see in tanks is dust and water. When you have a tank that's constantly being drained and filled, you have a volume of air that has to enter the tank to compensate for the loss in volume. So what we have on top here is a trap breather, and that prevents moisture and dust and dirt particles from entering the tank and contaminating the fluids that are in storage. Number 3 is a final filtration down to a very fine level, 4 microns, and we use that to make sure that the last part of the dust and dirt particles are taken out of the fluids, and that we remove the last dissolved water and anything like that before it enters an application. So where is Clean, Protect and Polish currently used? We use it across a wide variety of installations. So we see it, any industry that has a large amount of vehicles, a fleet that they don't want to bring to a normal refueling station, that they have their own tanks for storage, we can install Donaldson's Clean Solutions approach and use it to reduce their downtime. So that would be construction yards, mining sites, large agricultural farms, and truck and bus bases. And this is particularly aimed at people who don't have the luxury of downtime and engine failure. So now I'll run you through the contaminants that we see, the main proponents of failure and loss of efficiency in an engine. So what you see here is a sample of fuel that we took from a customer, and you might look at it and say, okay, it looks pretty clean. I can see all the way through the jar, and I don't see any large particles floating around. What we can't really see is the particles on a smaller level, which are shown here on the microscope images. So what you see up the top is the 20 micron piece, and that's actually considered quite a large particle for a fuel. Now, engines these days have a tolerance between 4 and 10 microns, and so what we aim to do is filter anything above 4 microns. When you have a 20 micron particle of dirt, dust, metal, anything like that, it can cause a large amount of damage in a cylinder head or on the pistons itself, and that's what we aim to remove with our clean solutions. So the main gist of this image is you can look at a fluid and you can think it's clean, but you really can't see the particles that matter the most. So here's a bit of a demonstration of how the particles look on a micron level. So at the larger end, you have a grain of table salt is about 100 microns. A human hair is about 80 microns. And the lower limit of human visibility is 40 microns. So everything below 40 microns is invisible to the human eye. And that's where we see smaller particles that can damage an engine, and everybody thinks they're safe from. So I'll run you through the main contaminants that are at this size level, which are dust and dirt, wear particles, water and rust, microbes, and additives and degradation. So the main proponent of failures in engines these days is dirt and dust particles. We filter air, we filter all fluids, and we try and remove as much of this as possible. So this is the main thing that we look at. So dirt is composed of 45% roughly mineral particles, and within that we have silica compounds. The silica compounds are on average about 3 times harder than stainless steels. And if you take that into account in an engine and you have a certain amount of dust going through your cylinders, that means that all the scratching that's caused by these is pretty damaging to the efficiency, and you can get a lot of failures just from that. Metallic particles come from pumps, valves, anything that moves that's a metallic component can generate a contaminant within a system during normal operation. And that's something that your filters should be catching on the application, but that maybe when a fluid is delivered you're not thinking about. So those fluids should be pre-cleaned before they enter an application. There's also the breakdown of rubber seals, O-rings and things like that. Those also were considered as wear particles. So the other contaminant that we really don't like at Donaldson is water and rust. So there's 2 types of water in fluids. It's emulsified water, and if you can think of it as finely dispersed water droplets in a fluid. The best way of thinking of it is mayonnaise is an emulsion, and that's what you don't want in your fluids. Free water is water that's settled out of solution, and it's sitting on the bottom of a tank because normally a fluid such as a fuel is a less dense fluid than water. And where do you drain your tanks from? You normally drain them from the bottom. So what you get coming out of the bottom of a tank first is always the water. Now we have microbes as well. These are things that grow in the tank, and they're also pretty damaging to an engine because they can block on-application filters quite quickly because they form large colonies. The main factors in this are that biodiesel, which is made from animal fats and plants, can act as a fuel for these contaminants, and the biomaterial can grow on these easily contained fuels. So ultra-low sulfur diesel as well is also a driver for bacteria and small particle growth in a tank, because the sulfur normally acts as a biocide within the tank itself, and the trend is towards low sulfur diesel at the moment. So in conjunction with free water, we see that on a tank you have a water fuel interface where the microbes like to grow, and down the bottom you can see a microscopic image of what that interface looks like when the bacteria has had time to grow, and that's most fuels in storage. So microbial growth, another fact that you might be interested in just as an economic kind of thing, is that microbial growth can consume up to 1% of your fuel per year. And when you're using millions of liters of fuel a year, that can add up to a significant cost. So the last thing that I'll talk about is additives and degradation, especially in third world countries. We see a lot of additives in fuel to keep the flow improved, to keep it from freezing, to keep it from degrading too quickly. And a lot of these things can drop out of solution when we have colder weather, when there's too much of them put in. They cause waxing and other things like this. So these jelly-like compounds that drop out can cause an on-application filter to block really quickly, and then you have to replace it, and your servicing is obviously increased. So another fact, oxidation rate increases 2.2 times per 10 degrees Celsius. So biodiesel stored at 20 degrees Celsius is on a borderline usability level after about 6 months. At 25 degrees Celsius, it's too degraded to use, and at 30 degrees Celsius, it's too degraded to use after 4 months. So those are kind of timelines that you can see affecting a mine or another construction yard or a trucking business, because their fuel has been stored for a long time and they don't refuel their tanks that often. The next thing I'll show you is the importance and effects, so regulations that relate to this, emissions, etc., and how they affect your engines. So the first regulations I'll talk about are off-road, and then I'll compare it to the on-road industry, which is trucking and buses. I'll tell you about equipment life, how it's affected by what we call the ISO cleanliness standard, how it affects your OEM warranties, injector damage, and engine wear. And then I'll show you some pictures of what Donaldson Clean Solutions looks like when it's applied to storage tanks in the field. So the first thing I want to talk about is the Tier 1 to Tier 4 regulations, which were brought in 1996. And when they started, we had a NOx level and a particulate matter level that were pretty high compared to today's standards. When we look at the trend, it's always been downwards. There's never been an upward trend in emissions. It's always going down, which means that engines have gotten more precise, the tolerances have grown smaller, and the requirements on an engine are much more stringent. So what we're seeing here is in 2011, Tier 4 regulations have brought about a 96% decrease in the amount of emissions for particulate matter and for nitrous oxides. When you compare that to the on-road industry, you can see that it's also a downward trend, and they follow a very similar pattern. So engines across the board have all grown in a more precise manner. The tolerances have decreased, and we're looking at more stringent requirements on the engines. So how do we measure the cleanliness of a fluid and say that for sure it won't affect the engine in the end? We have what's called an ISO cleanliness standard. So within the industry, this is universally accepted as the way we should measure fluids for cleanliness. There are other standards, but this is the most widely used in the filtration industry. What we have here is an ISO code, which consists of 3 numbers separated by 2 slashes. And the first number always represents the number of 4 micron particles or larger that are present in a fluid, and then 6 micron particles or larger as the second number, and 14 micron particles or larger are the third number. It gets a little bit confusing, so if anyone needs to come up and ask me afterwards, that's okay as well. I deal with this on a daily basis, so it's nearly off heart by me. But what we look at is there's a size range per each particle size plus that applies to each of these different codes. So when a fluid is delivered, what we typically see is a cleanliness level of about 22, 21, 18, which means when you bring it back here, you're seeing between 2 and 4 million particles of 4 micron plus, 1 and 2 million particles of 6 micron plus, and 130,000 to 250,000 of 14 micron plus. When you want to filter it, you want to get down to a specific target level that is specified by the OEMs for the fluids. What we like to look at is these target ratings. So here you can see the target rating for heavy gear oils. That's for hydraulics, heavy gear pumps, etc. They have a target rating of about 18, 16, 13. Hydraulic and transmission oils are also quite clean, 16, 14, 11. And on the more strict range, we have 14, 13, 11, which is the target rating for diesel fuels in current Euro 6 and Tier 4 engines. So all your newest equipment has a requirement that the fuel is about this cleanliness. What effect does this have on your warranties? Many OEM manufacturers won't actually honor the warranty if they can prove that your fluids were not clean enough and that the wear and tear caused in the engine was caused by misuse of fluids or contaminated fluids. So when you look at the target ratings, what you see for injectors is that we want to be at 14, 13, 11, and that's because the injectors are operating at about 2,000 atmospheres of pressure. Any sort of particle that enters those can damage them a lot. Vane pumps, etc., have a higher requirement. And you can see here that the 16, 14, 11 is less than 17, 15, 13, so that's okay to use, but that the 18, 16, 13 would end up damaging it with the larger amount of particles that are present in it. So the main takeaway from that is that pre-cleaned fluids and ISO cleanliness can prevent your manufacturers from voiding your warranty based off just of a dirty fluid, basically. What do we see when we look at it on a microscopic level? We're looking at injectors here. So this is the needle seat on an injector, where we can see a brand new injector that's just been bought, and after a few hours of operation with a dirty fluid, you can see that the needle has started to develop scratches from the particles hitting it at high speeds. This causes a bad spray pattern within the engine, and this decreases the efficiency of the engine because the fuel pattern burn is not optimal. So when you look at it from here, you can see what the injector spray pattern should look like on the left, which is a nice misted cloud, and what it typically looks like after it's being damaged, which is distinct streams of fluid that don't burn as easily. So what you really want is small particles. You know, in a dust explosion, dust only explodes because it's such a fine dust. It's the same with the fluid. Fluid will burn quicker and faster and more efficient as long as it's finer particles. When you have a damaged injector, you get a different burn rate. So what you want to avoid is having this different burn rate, and that your peak in engine power is as sharp as possible. So this is what we try and avoid when we're damaging injectors, when we prevent damage to the injectors. This is what it also causes on the engine side of things. So cylinders and heads can be damaged, pistons can be damaged, the seals on an engine can be damaged purely because an injector has been leaking fuel on one side of a cylinder wall. If the fluid decides to drip down one side and start to burn in one area, you get a concentration of heat, and this can cause melting of the piston rings that seal off the engine from the fuel side and the oil side. Typically what this causes is that fuel leaks into your lube, and lube leaks into your combustion. And when you have this, fuel is not as, it has a higher viscosity than, or not a higher viscosity, a less level of lubricity than a hydraulic fluid or an oil. And so what we cause is increased wear in engine bearings on the crank side, which means lower efficiency, lower power, and a higher fuel consumption overall. So this is what Donaldson's Clean Solutions looks like in the field. We've applied it across a large amount of applications. So what we see here is on the clean side, so remember I talked about clean, protect and polish. We had a clean side here and the protect side up here. And then on the other side of this tank there'll be a polish side, which is another manifold just like this one, which has a fine filtration to finish off. So what we see on the top of the tanks is the trap breathers, and they'll be used in many different industries. We had one farmer who wanted a mobile tank solution, so we installed a double head and we gave him two spin-ons. One is to absorb all the particles and one is to absorb the waters. So he was pretty happy with that. He got to run his machines for much longer in the field. And the last thing I want to show you is how it can actually affect the gold mine, because what everyone wants to see is a case study and the actual results behind this. So what we had was a European gold mine which was running on 23-hour production runs. They had a heavy dust environment, which means to us 50 to 100 milligrams per liter, and we were looking at 150,000 euro an hour on their production runs. They had two sets of tanks. So they had one set of fuel tanks, which were diesel tanks, which held 40,000 liters each, 3 of these. They had 1.5 million usage per year, and they were refilling their tanks every 2 days. So their cycle of fuel was quite high. The next step in this, they had 3 different oil types, which is the other set of tanks. They had a 10W, a 25W, and a heavy gear oil. And they were using 10,000 litre tanks for these. What does this look like when we apply the clean solutions? So what we want to look at is all the different factors that were affecting this mine, and we wanted to come up with a solution that would suit them, that they didn't have to have more downtime, that we reduce their downtime, reduce their part cost, etc. So what we applied was an 8-head manifold, which is 8 of the spin-ons that you saw in those manifolds earlier. We applied 7 trap breathers, which they had to change every 12 to 16 weeks. And we applied a 2-head manifold, which is the final level of filtration at the end. And in total it costs them about 12k a year. And when you see the savings, you're going to be kind of laughing at how little they spent in comparison to what they were costing in downtime. So their reduction in downtime was about 12 hours. They were having 12 unscheduled failures per year, and we reduced that by about 6 hours. So their service intervals went up 50 hours. They had from 250 hours per machine up to 300. And then they had less failures per injector per year, which is a smaller one, but it's also covering the entire cost of what Donaldson provided to this mine. So the 50% failure rate was from 6 injectors failing per year down to 3. And when you compare this, you can see the differences in the cost versus the savings. And when you graph it out, you can really see the difference. So the savings totaled about 2 million a year, and the cost of Donaldson's approach was about 12,000 a year. So just a bit of perspective on that is nice as well. I'll show you a video of the trap breather in action. It's always nice to have a little video thrown at the end. So you can really see in the humid environment, the trap breather working to remove the water that's trying to enter the tank. And what we normally see is that as a mechanism, the water dripping off of these breathers also tends to remove the dust and dirt particles. So it's almost a self-regenerating filter, if you might. Yep, that's Donaldson's Clean Solutions approach. I hope it was enjoyable, and if you'd like to visit us, we're at booth 188. Thanks very much, guys.